Welcome to this chapter on how computers represent information. In this lecture, we will move from the most basic idea in digital hardware, an on or off state, toward the richer representations that programmers use every day. We will examine abstraction, bits, bytes, binary numbers, hexadecimal notation, storage prefixes, and floating point values. The goal is not simply to memorize conversions. Instead, we want to understand why these representations exist, what each one makes easier, and what trade-offs each one introduces. By the end, you should be able to connect a human-readable idea to the patterns stored inside a computer. That connection is foundational for programming because every variable, character, image, sound, and measurement eventually depends on choices about representation. As we work through the slides, keep asking one question: what information is preserved and what detail is being hidden? Abstraction from Bits to Meaning by the Programming Professor. Our outline begins with abstraction, the process of reducing detail so that a problem becomes easier to understand or generalize. We then examine bits and information, because computers ultimately store data as patterns of zeros and ones. From there, we study unsigned binary numbers, including counting, conversion, addition, and overflow. Next, we compare binary with hexadecimal, octal, and other number bases. Finally, we look at the scale of modern storage and the special challenges of floating point numbers. This sequence is intentional. We first discuss the idea of hiding detail, then identify the low-level building blocks, and only after that build more convenient numerical systems on top of them. The final section brings us back to programming practice by showing how range, storage, and precision affect the behavior of real programs. Think of the lecture as a climb from hardware states to useful abstractions. Abstraction is one of the most important ideas in computing. It means reducing information and detail so that we can focus on the features relevant to the current task. The graphic on this slide shows the same information at several levels. At the bottom, the computer sees a sequence of bits. Those bits can be interpreted as numbers, and the numbers can be interpreted as characters. At a higher level, those characters form a message that makes sense to a person. None of the lower layers disappear. Each layer provides the foundation for the next one. The benefit is that we do not need to think about every switch when reading a message. As programmers, we constantly choose an appropriate level of abstraction. We work with strings instead of individual bits, functions instead of repeated instructions, and data structures instead of isolated memory locations. Abstraction applies to instructions as well as data. A programmer may write a high-level function that expresses an operation in a form that is readable and reusable. A compiler translates that source into assembly language, which exposes more of the machine's operations. An assembler then translates the assembly instructions into binary machine language. Each step moves toward the level that the hardware can execute directly. The important point is that programmers normally do not need to write the binary themselves. High-level languages provide abstractions for procedures, conditions, values, and objects, allowing people to reason about the problem rather than the electrical details. Tools perform the translation between levels. When debugging or studying performance, however, it can be useful to understand that these levels exist. A simple line of source code may eventually become several lower-level operations, and the translation process connects human intent to machine behavior. Now we reach the smallest vocabulary used by digital computers, the bit. A bit can have one of two values, 0 or 1, corresponding to two distinguishable hardware states. 8 bits make a byte, giving us 8 positions that can each be 0 or 1. The patterns stored in those positions can represent many kinds of information, but the computer does not automatically know whether a pattern represents a letter, a number, a color, or part of an audio file. That meaning comes from an encoding convention and from the program interpreting the data. This is a useful distinction. Storage is physical while interpretation is conceptual. When we say that computers store everything as bits, we are describing the underlying representation. We are not saying that every piece of information has the same meaning. Programmers choose and document the rules that turn bit patterns into useful values. Characters require an agreed-upon encoding so that different programs and devices can interpret the same bits consistently. In the example, the character A is associated with the ASCII value 65, which is stored in binary as 01000001. ASCII is compact and works well for a core set of English letters, digits, punctuation marks, and control characters. However, modern communication requires far more characters than ASCII can provide. Unicode extends the same general idea to support many writing systems, symbols, and emoji. The key lesson is that the bit pattern does not inherently mean A. It means A because an encoding standard assigns that interpretation. If two systems use different encodings, the same bits may produce different displayed characters. This is why character encoding matters when reading files, exchanging data over networks, or processing text in a program. Reliable software depends on using compatible conventions. Binary counting is based on place values, just as decimal counting is. The difference is that binary has only two symbols, 0 and 1. In a 4-bit number, the positions represent powers of 2, 8, 4, 2, and 1. A 1 in a position selects that position's weight, while a 0 leaves it out. Therefore, 1111 in binary represents 8 plus 4 plus 2 plus 1, or 15 in decimal. When a binary position reaches 2, it resets to 0 and carries 1 into the position to its left. This is the same principle as decimal counting, where reaching 10 resets a digit and creates a carry. Understanding place values is more useful than memorizing isolated conversions, because it lets you reason about any binary pattern. It also explains why adding one bit doubles the number of possible patterns available. The pseudocode on this slide describes a repeatable method for converting a decimal number into binary. The process repeatedly examines whether the current number is odd or even, records the corresponding bit, and divides by 2. The recorded remainders are assembled in reverse order to produce the final binary representation. Notice that the example is written as pseudocode rather than as a particular language. It describes the algorithm clearly without requiring syntax from C, Java, or Python. This is a valuable stage in programming because it separates the logic of a solution from the details of implementation. The 4-bit example also reminds us that a fixed number of bits limits the range of values. With 4 unsigned bits, the largest representable value is 15. When designing a program, we must choose enough storage for the values we expect, while recognizing that more storage has costs. Binary addition follows the same right-to-left process used in decimal addition, but the possible digit values are smaller. In the example, 0111 and 0110 represent 7 and 6. Starting at the right, we add each column and carry whenever the sum reaches 2. The result is 1101, which represents 13. The carry rules are simple. 0 plus 0 is 0, 1 plus 0 is 1, and 1 plus 1 produces 0 with a carry of 1. The carry can continue into the next column when 3 ones are involved. This leads to overflow. If 4-bit numbers produce a result such as 10000, the result needs 5 bits and cannot fit in 4 positions. Overflow can affect counters, financial calculations, array indexes, and security-sensitive code. Programmers must understand the range of the chosen data type and decide how overflow should be handled. Hexadecimal, or base 16, is popular because it gives us a compact way to write binary. 4 binary digits have 16 possible combinations, exactly matching the 16 symbols used by hexadecimal, 0 through 9 followed by A through F. In the example, the binary pattern 11000111 becomes C7. We simply group the bits into sets of 4 and translate each group. This is easier to read than a long string of zeros and ones, while preserving the same information. Hexadecimal appears frequently in memory addresses, machine code, color values, and debugging tools. A byte can be written using 2 hexadecimal digits. The notation is compact, but the underlying data has not changed. Hexadecimal is another abstraction layer. It hides some visual detail while keeping the binary structure easy to recover. Learning the 4-bit mapping provides a practical bridge between human-readable code and machine-level data. Binary, hexadecimal, octal, and decimal are all examples of positional number systems. In a positional system, each digit is multiplied by a power of the base, and the products are added together. Base 2 uses powers of 2, base 8 uses powers of 8, base 10 uses powers of 10, and base 16 uses powers of 16. Octal is useful because each octal digit corresponds to 3 binary bits, while hexadecimal digits correspond to 4. The slide also shows a number in base 5 to emphasize that the same place value idea works for any base. The symbols and weights change, but the reasoning remains the same. When you encounter an unfamiliar base, identify its digits, write the place values, and evaluate the weighted sum. Number bases are different ways of naming the same underlying quantities. As computer systems grew, people needed convenient names for very large quantities of bits and bytes. The slide shows powers of 2 that roughly correspond to kilo, mega, giga, and tera. The approximation comes from the fact that 2 to the 10th power is 1024, which is close to 1000. Similarly, 2 to the 20th power is a little more than 1 million, and 2 to the 30th power is a little more than 1 billion. In everyday technology discussions, metric prefixes are often used informally for these binary quantities. The IEC prefixes kibai, mebai, jibai, and tebai make the powers of 2 meaning more explicit. These distinctions matter when comparing storage capacity, memory, and file sizes. It is also important to distinguish bits from bytes. Lowercase b commonly means bit, while uppercase b means byte. Careful terminology prevents confusion when discussing capacity or data transfer rates. The terms bit, byte, and word describe increasingly useful groupings of storage. A bit is a single binary choice. A byte contains 8 bits and is a common unit for characters and memory. A word is a fixed-size group that a particular processor handles naturally, although its size depends on the system. More bits provide more possible patterns. That can mean a larger range of integer values, more colors in an image, more samples in an audio signal, or finer precision in a measurement. The trade-off is that more bits require more storage, bandwidth, and sometimes more computation. When you see a storage specification, ask what is being measured and what unit is being used. Capacity describes how much data can be stored, while a transfer rate describes how quickly data moves. The same prefixes can appear in both contexts, but the concepts are different. Floating point numbers are designed for values that may include a fractional part, such as temperature, distance, or mass. The slide presents the idea using a significand and an exponent. In normalized binary scientific notation, a value has the form 1.f multiplied by a power of 2. The significand carries the meaningful digits, while the exponent controls the scale. This structure allows a fixed number of bits to represent values across a wide range. Integers are usually a natural choice for things we count, while floating point values are useful for things we measure. However, floating point representation introduces behavior that programmers must understand. A fixed number of bits cannot represent every real number exactly. The system stores an approximation, and computations can accumulate small differences. The representation balances range and precision, but it is not a perfect substitute for real number arithmetic. Binary fractions make the limits of floating point precision easier to see. The digits after a binary point represent weights of 1/2, 1/4, 1/8, 1/16, and so on. Some decimal fractions can be represented exactly, while others fall between available binary values when only a limited number of fraction bits are stored. The slide uses 0.8 as an example of a value between nearby representable points. The computer chooses the closest available approximation, which may be slightly above or below the intended value. Increasing the number of fraction bits gives the system more choices and usually improves precision, but it also requires more storage. This explains why a program can produce a result that differs slightly from a hand calculation. For graphics or physical simulation, that may be acceptable. For money or exact counts, a different representation may be more appropriate. Representation choices should match the problem's requirements. Let us bring the chapter together. First, abstraction allows us to work with useful concepts without constantly exposing every implementation detail. Second, bits are the foundation for all digital data, but encoding conventions determine whether a pattern is interpreted as a character, number, image, or something else. Third, binary place values explain counting, while hexadecimal and octal provide compact ways to write binary. Fourth, the number of available bits determines range, capacity, and the number of distinctions a system can represent. Finally, floating point formats extend the range of measurable values, while accepting that some values will be approximate. These ideas form a connected ladder from hardware states to software meaning. As you write programs, ask what representation best fits the problem, what values it can hold, and what errors it may introduce. Understanding representation makes computer behavior easier to predict, test, and explain. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.